Hey everyone, welcome to 4.6 Numerical Integration. We're going to start off with the trapezoidal rule. Now I've seen this a couple of times already on some practice AP tests that we've had. The free response questions have said, approximate the area under the curve using the trapezoidal rule, or using a trapezoid, or using some sort of trapezoid. I don't remember the exact wording, but they said something with trapezoid. And I'll say, okay, I logged that in my brain, and now we're going to talk about it here today. Okay, so we want to be able to find out the area underneath this curve, and we're going to use the trapezoid method to do that. And you say, I don't know what that is, Mr. Bartman, but you say, actually, I do know something about trapezoids. Okay, so hang on to that thought before we actually go on and find the area underneath here using trapezoids. This method helps out for two cases. One, what if you can't find the integral? What happens if it's so complex that you just say, I can't do it? Would it be easier just to graph it and then find an approximation that might be close enough? The second thing is, what happens if the test just says, use trapezoid approximation? I don't need the exact answer, I just want the trapezoid approximation. Okay, well then this seems like a pretty good method, right? Okay, so let's go back and let's just remember what we know about a trapezoid. Here's what you remember about a trapezoid. I remember that, first of all, most of the time, you probably remember trapezoids looking like this, but this is the way they're going to be oriented for what we're looking at, so let's just use this. Trapezoid, the area of a trapezoid is 1/2, add up the bases, times the height. So it's really like find half of the bases, find like the middle, if you will, and then multiply by the height. So it's kind of like you take off the top and the bottom, you just kind of make it into this rectangle, right? And so this line is kind of like base 1 plus base 2 divided by 2. So that's going to be this thing, okay? And then we just find the area, okay? Seems like a good idea. Now let's see if we can use that here. So if I were to say between x0 and x1, I could make this little trapezoid right here. Okay, it's almost exactly on that line. And then we go to x1 to x2, I could make this trapezoid right there. And that seems like it's almost on that line. And then I can go from x2 to x3, and I can go here. Now we're a little bit off, but that's a pretty good approximation, right? So I can find the area of this one and this one. And I can find the area of this one in the middle. And then if I want to find the area under the curve for all of them, I would just add the blue and orange areas together, right? So let's just say this is area 1, area 2, and let's call this one area 54. So then you can say the area under this curve, area would equal area 1 plus area 2 plus area 54. Okay, so then you just add up all the different trapezoids, and then you really have it. Okay, so let's go down and let's look at the actual trapezoid rule itself. The trapezoid rule itself says, and this is theorem 1.6 in your book, the trapezoid rule, let f of x be continuous on AB, on the closed interval AB, right? Good. The trapezoidal, let's see if we can maybe get that a little bit clearer for you. There you go. That's much better. So the trapezoidal rule for approximating the integral from a to b f of x dx is given by the following. The integral of f of x dx is approximately equal to b minus a, and that's this b and this a, right? So we're using both of those, over 2n, and then that's going to be times f of x naught plus 2 f of x1 plus 2 f of x2 plus dot 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 f of x to the, or fx sub n, where n is the number of trapezoids. Okay, so the first one you only have 1, and then we've got a 2 here, and we've got a 2 here, and we've got all these 2's in all our middle terms. The only time I have 1 here and 1 here is at the first and last term. You say, well, why do I have to have 2 of them? That doesn't seem to make much sense to me, Mr. Bartman. And I say, don't worry, kids, listen to me. On this triangle that was blue, A1, how many times did I have to use this height? Once, right? So I use that one for one of my bases, right? And then on area 54, I use this one as one of my heights, right? I did. So in fact, I have to use that twice. Why don't I have to use the first one twice? Well, because it's only part of one trapezoid. This one is part of one trapezoid. This is the middle of 2 trapezoids. That's why we have 2. This one's in the middle of 2 trapezoids. That's why we have 2. This one's at the end, so it only has 1. Okay? Kind of makes sense. I don't have to do anything with the first and last ones. They're just going to be put in there. And the ones, all the ones in the middle are going to have two because they're going to use two of them. Interesting. Anyway, what we're going to do is let's go over here to Desmos here, and let's just a quick look at what Desmos has to say about this. So we have a couple of sliders here, and I'm kind of covering up a couple of them, but it's the function f of x equals x cubed. All right, so if we zoom out, we can kind of see, oh yeah, sure enough, that looks like an x cubed. And now we can kind of change what a is, right? So I can move a all around, and let's just make a 0. Seems to be okay. And then we're going to make b something larger than that. I can't make, if I goes negative, nothing happens, all right? So let's just make b larger. Let's make b right about here. Okay, so now you can see that here we have one trapezoid where n equals 1. This trapezoid is going to approximate the area underneath this curve, but that does not look very accurate now, does it? No, not very accurate at all. But what happens as we increase the n's? Oh, look, already by 3, it looks way better, right? We have a little bit area above. I can't really tell. That one's also above, right? So we know that our answer here, our area is going to be an over approximation, right? We're going to have more than the actual area that it would be there. Okay, but as I start to increase my n's, look what happens. Look at the number of trapezoids increases. They get closer and closer probably to the exact answer, right? So you see how, actually you can see down here, n equals 3, n equals 1. We can say this is probably going to be our total area, 4.1, pretty high. As I start to go this way, it's going down to 2.3, 2.1, 2.12, 2.10, 2.09, all the way up to as high as I can go. I can get up to 25, and it goes 2.09. I'm not saying that's accurate, but I'm saying it's probably a lot closer than when we're at 4.1, right? So the more trapezoids you have, the better it's going to be. All right, so this is kind of a good interactive. I will actually maybe put this on, see if I can do something for you. That way, if you want to check some things out, I'll just make a link to this on Google Classroom. All right, sounds good. Now, let's just go through and let's do one example. I'm not sure if I'll actually end up doing both these examples. We'll see, because the second one's going to be kind of tedious. So we'll see. Maybe we'll get started on it, and then we'll say, finish it for homework or something like that. So we'll see what happens here. All right, so what we're going to do is we're going to approximate the integral from 0 to pi of sine x dx. Notice how it's sine x dx, otherwise that wouldn't be a function, it wouldn't make any sense. Okay, now could you actually take the integral and find the exact area? Sure you could, of course. But let's just say it says approximate using the trapezoidal rule, and that's what I'm asking you to do. Okay, and I'm even telling you how many trapezoids are we going to have? We're going to have 4, and then we're going to have 8. Okay, so that means I need to have 4 trapezoids. Alright, so I should be able to add 4 things together. Now let's go back and let's actually use our trapezoidal rule, which remember, we're going to say the integral from 0 to pi of sine x dx is going to be about b minus a, which is going to be pi minus 0, all over 2n. So it's going to be 2 times 4. Now do you have to write all this out? No, but I'm kind of showing you where everything is at, okay, why we're doing all this stuff. So then that's going to be times, we have to think about, okay, if I have my function, and that's going to be sine of x from 0 to pi, that's going to be doing one of these, right, where this expertly made it to be 1. Okay, so I need to have 4 trapezoids. So I have 1, 2, 3, 4. So I should have one that goes here, and it's going to go that. Looks good. And I've got one that goes here. I've got that. I've got one that goes here. It looks like that. And I've got the last one looks here. Okay, so it looks like it's probably going to be an underestimate from what I'm saying, because we're missing this little part. 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 Okay, so if I'm at 0 to pi, I know this is pi over 2. I know this is going to be pi over 4. I know this is going to be 3 pi over 4, right? Because I just split it up into 4 parts. It's like 1/4, 2/4, 3/4, 4/4 of pi. Okay, so I will say that my first spot is going to be f, or sine, of 0. My first one. Okay, plus I have to do 2 sine of pi over 4, plus 2 sine pi over 2, plus 2 sine, oh boy, I'm really running out of room here, 2 sine 3 pi over 4, dang it, and then I got to do plus 1 sine of pi. Okay, remember, because if I'm talking about this trapezoid, which is really a triangle, but we're going to say it's a trapezoid because it kind of gives us the same thing. Okay, I've got, this counts as 1, and then I need 2 of these because this one counts for this triangle, or that trapezoid, and that trapezoid. Pi over 2 counts for both trapezoids, so that's why we get those 2's again. Okay, so now let's see if we can maybe simplify this up. Pi minus 0 is pi, 2 times 4 is 8, so it's going to be pi over 8. Now let's see if we can just figure out all those numbers. Sine of 0 is just going to be 0. Pi over 4 is going to be square root of 2 over 2, so it's going to be 2 times square root of 2 over 2, plus pi over 2 is going to be 1, which is 1, 2 times 1, putting that 2 out in front, plus the next one should be sine of 3 pi over 4. I'm guessing that's going to be 2 times square root of 2 over 2, one more time, plus sine of pi, which is going to be 2 times 0. Okay, let's simplify that just a little bit further. Let's just keep the squiggly mark, and we're going to say that squiggly mark is about pi over 8. I'm going to drop the zeros because they don't really matter, right? 2 times that is going to be square root of 2 plus 2 plus square root of 2. Okay, and then after that, do you think you could probably just put that in your calculator and solve? Probably, yeah, because I could say that's about equal to pi over 8. Then we have 2 square root 2 plus 2, and then we can say that's approximately equal to pi over 8, 2 square root 2 plus 1, and then that would just be pi over 4 and 1 plus square root 2. Okay, so we can write that, and then you can also go through and say this is my answer, and that would be approximately equal to 1.896. Okay, 1.896. Alright, let's do it with n equals 8 real quick. Holy cow, this is starting to take a little bit while. We're just going to set this up and maybe you can finish it. Okay, so we're going to do the same thing with n equals 8. We can say that integral from 0 to pi sine x dx is going to be about pi minus 0. Hey computer, there we go. Pi minus 0 over, and we're going to go 2 times 8 this time, right? Because we have n equals 8. And then that's going to be times f of 0, which is going to be sine 0, plus, now we're going to just break these up into even smaller ones, right? So now we're going to have plus sine of pi over 8 plus, sorry, it should be 2 sine pi over 8 plus 2 sine pi over 4 plus 2 sine 3 pi over 8, and so on and so on. Okay, and then you can just go through and do this. So you see, what's going to most likely happen is on the AP Calc test, they're going to ask you probably about 4 as a maximum, I'm guessing, because they're not going to ask you to do all this stuff by hand. If you can do 4, you can do 8. Okay, but just to kind of give you an idea, when you go through this one, let's just say this is going to be approximately 1.974. So it's going to get a little bit closer after you do that whole thing. Okay, so see if you can do sine of dx when you have 8 trapezoids, and see if you come with about 1.974. Alright, good luck.